If you fold a piece of paper so that 2 points touch and then poke a hole in it with a pencil, in space-time, a wormhole is like that pencil, creating a straight path between 2 distant points. If this concept can be realized, can we use wormholes for interstellar travel? This story begins here, with Saturn, the beauty of our solar system. It has a unique moon that hides secrets exclusive to it, known as Titan. Titan is shrouded in a thick, hazy atmosphere, and its surface challenges our understanding of moons. Beneath its orange veil lies a landscape not made of water, but composed of liquid methane and ethane. Titan is the only place in the solar system where stable liquids exist on the surface, but these oceans and lakes are not made of water. They consist of hydrocarbons. These substances are both strange and deadly on Earth. If you are fortunate enough to stand on the shores of Titan's Kraken Sea, what first catches your eye is an ocean larger than 193,000 square miles. Its area is larger than that of Jilin province. This is a sea floating with liquid methane, and it has an eerily calm surface. The sky is perpetually covered in orange haze. The missions of Cassini and Huygens discovered these astonishing features, revealing that the lakes and oceans here have coastlines that change with the seasons, and may even show signs of cryovolcanic activity. These volcanoes do not spew lava but rather cold materials, with methane and ethane condensing and falling from the sky, carving out river channels, filling puddles, and then evaporating. This initiates a new cycle, but how is this cycle on Titan maintained? Methane in the atmosphere should be broken down by sunlight, yet it persists. Does Titan have an underground ocean? A reservoir that replenishes its surface with fresh methane? Join us on this oceanic journey to explore Titan and delve into the discoveries of Cassini and Huygens, uncovering its wondrous aspects. Before the Cassini-Huygens mission, our understanding of Titan was quite limited due to its size and dense nitrogen atmosphere. Cassini changed all of that. It revealed that Titan is a world full of dynamic changes, with complex geology and atmospheric processes. The mission made groundbreaking discoveries about Titan, the most notable of which was the confirmation of lakes and oceans composed of liquid methane and ethane. These hydrocarbon bodies are replenished by the thick nitrogen-rich atmosphere, forming a methane cycle similar to Earth's water cycle. This cycle is not the only Earth-like feature on Titan. Near the equator, there are vast dune fields resembling Earth's deserts. However, these dunes are not made of silicate sand, but consist of solid water ice coated with organic compounds that have precipitated from the atmosphere. When the Huygens probe landed on the surface of Titan, it conducted detailed measurements and captured images, allowing us to see this alien world directly for the first time. The probe's data indicated that the terrain here is formed from both liquid and solid hydrocarbons. Perhaps most captivating is the evidence of an underground ocean beneath Titan's icy crust. Cassini's gravity measurements suggest that this hidden ocean may be a mix of water and ammonia, placing Titan among celestial bodies that could potentially harbor life. We will explore this topic in detail later. Long-term observations have also recorded seasonal changes on Titan. Each season lasts about 7.5 Earth years. Cassini documented the transition from fall to winter in Titan's southern hemisphere, as well as the onset of summer in the northern polar region. These seasonal changes affect the methane lakes and oceans, giving us a better understanding of Titan's dynamic climate. Although Titan sounds quite strange, in some respects, it is one of the most habitable worlds in the solar system. Titan's nitrogen atmosphere is so dense that people could walk on its surface without a spacesuit, only needing an oxygen mask and cold weather gear. Its surface temperature is around -290 degrees Fahrenheit. The thick atmosphere also means that raindrops fall much slower than on Earth. Raindrops on Earth fall at about 20 miles per hour, whereas scientists estimate that raindrops on Titan fall at about 3.5 miles per hour, roughly 6 times slower than on Earth. However, let's return to the oceans and lakes composed of hydrocarbons. The 3 largest oceans on Titan, Kraken Sea, Ligeia Sea, and Punga Sea, are located near the North Pole and primarily consist of liquid methane and ethane. Recent analysis of Cassini's dual-frequency radar data has given us new insights into these oceans. Unlike single-frequency radar, dual-frequency radar sends signals from the spacecraft that are recorded after reflecting off the surface. This method enables scientists to collect more detailed information about surface composition and characteristics. A research team led by Cornell University used Cassini's multiple flybys to assess the composition and roughness of Titan's ocean surfaces. The results show that the surface of these oceans exhibits significant variations depending on their latitude and proximity to rivers and estuaries. For example, the southernmost Kraken Sea has the highest dielectric constant, indicating differences in composition. Interestingly, despite the complex surface conditions of these oceans, they are mostly calm during flybys. Radar data shows that the wave heights in Kraken Sea, Ligaea Sea, and Punga Sea do not exceed 1/10 of an inch, while near coastal areas and estuaries, wave conditions are slightly rougher, reaching up to 1/5 of an inch. These variations suggest the presence of tidal flows similar to those on Earth. Another interesting discovery is the difference in water composition between rivers and open oceans. Rivers flowing into Titan's oceans are primarily composed of pure methane, while the oceans themselves are rich in ethane, resembling the mixing of freshwater rivers with saltwater oceans on Earth. This highlights the dynamic nature of the hydrocarbon cycle and Earth-like characteristics. The methane cycle on Titan is very similar to the water cycle on Earth, as methane clouds form in the thick nitrogen atmosphere, leading to methane rainfall that fills rivers and oceans. The rain is mainly composed of pure methane, but also contains trace amounts of ethane and other hydrocarbons, affecting the composition of the oceans. The tranquility of Titan's oceans and their unique compositions provide us with rich information about the satellite's meteorological and geological processes. Ongoing analysis of Cassini's data continues to provide us with more insights into Titan's climate and the possibility of life. However, the methane in Titan's thick atmosphere is constantly being broken down by sunlight. The persistent presence of this gas has long puzzled scientists, leading to many theories. One main hypothesis is that beneath Titan's methane clouds lies an underground ocean, a reservoir mixed with water and ammonia, which could be an important source of materials. Recent studies, by analyzing Cassini's gravity field measurements, have provided new insights into Titan's internal structure. Scientists concluded that the thickness of Titan's ice crust varies, which may indicate that its internal environment is active and undergoing continuous convection. This convection may help move underground water, forming liquid regions. The materials in these regions could erupt in the form of cryovolcanoes, breaking through the ice layer. Cryovolcanoes could erupt and release methane into the atmosphere, replenishing the gas reservoir. Studies suggest that Titan has experienced several significant outgassing events over its 4.5 billion year history, with the most recent occurring around 500 million years ago, triggered by convection within the ice shell. Earlier events were caused by similar processes in its core and ice shell, indicating that Titan has a dynamic geological history. Cassini's gravity field measurements played a crucial role in these discoveries. By analyzing subtle changes in the radio signals while the spacecraft orbited Titan, scientists could infer the existence of an underground ocean. These measurements indicate that Titan's shape changes over time, and the extent of these changes is significantly greater than what you would expect from a solid body. If methane is indeed replenished from an underground ocean, it suggests that Titan has a very active and complex internal structure. This ongoing geological activity could also influence Titan's potential habitability, making it a primary target for future exploration. Titan's geological activity is a fascinating area of research that reveals the strength of its rocky core, which plays a crucial role in geological dynamics. Studies show that Titan's core rocks are quite solid, capable of withstanding the kinds of fractures and faults seen in Earth's tectonic activity. However, the immense pressure from the overlying ice and fluid layers can still lead to significant geological activity. Despite the different nature of their interactions, the interplay between rocks and the underground ocean is a key area of study. On Earth, hydrothermal vents create an environment where water and rock interact, supporting various ecosystems. If similar interactions occur on Titan, it could impact its habitability and the potential for life. Cassini detected organic compounds in Titan's atmosphere, indicating that complex chemical processes are occurring there. Titan has long captivated scientists due to its Earth-like features and the possibility of extraterrestrial life. Its thick atmosphere, liquid oceans, and underground oceans offer enticing possibilities for the existence of life. One of the most intriguing aspects of Titan is its complex organic chemistry. Cassini-Huygens missions revealed that its atmosphere is rich in organic molecules and features a dynamic cycle similar to Earth's water cycle, providing the necessary raw materials for the formation of life. This year's research focuses on the possibility of organic molecules entering this underground ocean. Impacts from comets and meteorites could serve as a mechanism for delivering organic materials through the ice shell to the underground ocean, generating heat that melts the ice. Organic compounds could then mix with the ocean below, potentially creating a rich environment supportive of life over decades. However, the idea of life existing on Titan also faces challenges. The extreme cold and lack of sunlight make it unlikely for life as we know it to exist on its surface. Additionally, recent research suggests that Titan's ice shell may be too solid, and that geological activity is not very active, which could limit interactions between water and minerals that are crucial for life. Despite these challenges, Titan remains one of the most promising places in the solar system to search for life. The complex interactions between organic chemistry, liquid methane oceans, and underground oceans offer many opportunities for the evolution of life, even if such life is different from anything we have seen before. NASA's Dragonfly mission will continue exploring Titan's potential for life in the coming years. This innovative drone, set to launch in 2028, will study Titan's surface and atmosphere in unprecedented detail, providing vital data to confirm or deny the existence of life. The mission will primarily analyze the composition of organic materials, study weather patterns, and search for signs of prebiotic chemistry. The Dragonfly lander is the heart of this mission, an advanced instrument designed to analyze the chemical composition of surface materials. A digital storage system is crucial for studying the prebiotic chemistry of life on Titan. This instrument will analyze surface material samples, detecting organic molecules that serve as the building blocks of life. By studying these molecules, scientists will help uncover the chemical processes that may lead to the emergence of life, just as they did on early Earth. The instrument ionizes the sample material by bombarding it with energy, causing the atoms to become charged. These charged atoms are then detected by sensors to generate detailed chemical fingerprints of the samples. This process is always dynamic, with a random storage capability that can identify various organic compounds and their distribution in different surface environments. To collect samples, the Dragonfly is equipped with a drill designed to gather complex organic materials. This drill will extract small samples from the surface, which will then be analyzed by the storage instrument placed in the lander's loft. The samples will be prepared for analysis by evaporating in an oven or being irradiated with a laser. Dragonfly will be able to fly across different regions of Titan's surface, which is one of its significant advantages. This mobility allows it to explore various geological environments, from methane lakes to organic-rich dunes. At each location, it will use the storage system to collect unique samples for analysis. In addition to the storage system, Dragonfly will carry other scientific instruments to measure atmospheric conditions, weather patterns, and surface characteristics. This comprehensive suite of instruments will provide an overall picture of Titan's environment, attempting to further expand our understanding of Titan's habitability. Searching for life on Titan is not just about finding microbes or complex organisms, but understanding the fundamental processes that could lead to the origin of life, helping us comprehend the conditions necessary for life to emerge in the universe. We look forward to the upcoming Dragonfly mission and the new discoveries it will bring. These discoveries will not only reveal Titan's habitability potential, but also help us understand other celestial bodies and exoplanets in the universe. Next, I will share with you the latest discoveries in the journey to understand the universe. Imagine a newly born universe just a few 100 million years old, a time when the first galaxies are starting to form. Thanks to the James Webb Space Telescope, we have made groundbreaking discoveries. As we return to an ancient era, every tiny point of light in the universe before you is a galaxy, a massive cluster of stars, planets, and mysterious objects. Among these countless galaxies, Some are incredibly distant, with their light taking billions of years to reach us. Studying these distant galaxies is crucial because it helps us understand the early stages of the universe's evolution and the formation of cosmic structures. Just this year, astronomers utilized the James Webb Space Telescope to delve into the early universe, discovering galaxies that existed over 13 billion years ago. Among these, you'll find galaxies with redshifts between 9 and 11. But what does this mean? Simply put, redshift is a measure of how much the light from these galaxies has been stretched by the expansion of the universe. The greater the redshift, the older the time at which we observe the galaxy. The light from these newly discovered galaxies began its journey when the universe was less than 1 billion years old, at a time when our Milky Way was just beginning to form, with only the first stars illuminating the cosmos. These galaxies are not only distinct, but also incredibly young, offering us a glimpse into the universe's formative era. So, how did galaxies like our Milky Way originate and evolve over billions of years? Let's search for answers in the depths of the universe. Hidden among countless stars is the galaxy HSC 43833, a galaxy with a redshift of 8.76, bringing us back to an era when the universe was less than 600 million years old. The light traveling across the vast universe provides us with valuable information about the early stages of galaxy formation. Upon deeper exploration, astronomers discovered the galaxy HSC 16943, which is even farther away, with a redshift of 11.4. This galaxy is one of the most ancient galaxies ever observed, having emitted light when the universe was only 400 million years old. Studying such distant galaxies helps us understand the processes that led to the formation of the first stars. Next is the galaxy MAX 0647, which presents the unknown of the universe before us. Its redshift parameter is 10.17, and the light from this galaxy took over 13 billion years to reach us. Its discovery benefited from the powerful capabilities of the James Webb Space Telescope, revealing its complex structure and providing us with a deeper understanding of the early universe. But what is redshift, and why is it so important? Imagine a car driving away from you. Just as the taillights of the car appear redder as it moves away, the light from distant galaxies is also stretched and shifted toward the red spectrum. The higher the redshift, the more distant and older the galaxy is. Redshift is an essential tool for astronomers, enabling us to measure the distance of these galaxies and, thereby, determine their ages. The light from these galaxies began its journey billions of years ago, providing us with snapshots of the early universe. By studying galaxies with different redshifts, we can piece together the story of the universe's evolution. Distant galaxies are not just remote celestial bodies. They are time capsules that allow us to glimpse the early universe. These discoveries answer fundamental questions about our existence. How did the first galaxies form, and what processes drove their evolution? What do these findings tell us about our home, the Milky Way? The discoveries of these distant galaxies benefit from two important observational projects that utilize the advanced capabilities of the James Webb Space Telescope to explore the universe more deeply than ever before. The first project utilized discretionary time, led by principal investigator Pablo Arrabal, focusing on observing high redshift galaxies. This project aims to study the early universe and search for galaxies formed just a few hundred million years after the Big Bang. By targeting specific areas of the sky, the DD2750 project successfully identified several ancient galaxies, including HSC 43833. The second project is part of a comprehensive observational initiative led by Principal Investigator Shankar. This project aims to perform detailed spectroscopic studies of known high redshift candidates. The GO1433 project has played an essential role in confirming the redshifts of these galaxies and studying their characteristics in detail. As part of this project, the research team observed two additional celestial bodies, obtaining valuable data about their composition and structure. The James Webb Space Telescope used its two most powerful instruments, the near-infrared spectrograph and the mid-infrared instrument, to conduct these groundbreaking observations. Let's take a closer look at how these instruments work. The near-infrared spectrograph is designed to simultaneously acquire spectra from multiple galaxies. This instrument can analyze the light of galaxies to determine their chemical composition, temperature, density, and redshift. This instrument is crucial for studying the detailed characteristics of galaxies and understanding their evolution over time. The mid-infrared instrument operates in the near-infrared wavelength range, which is ideal for observing distant galaxies. By dispersing the light, this instrument creates detailed fingerprints for each galaxy, revealing their unique features. The near-infrared spectrograph has a different but complementary role, capturing high-resolution images of galaxies, allowing astronomers to study their morphology and structure. This camera is particularly effective in observing faint and distant objects, making it indispensable for identifying and analyzing high-redshift galaxies. The wide field of view of the near-infrared spectrograph enables it to capture large swaths of the sky in a single image, a capability that is crucial for survey projects like DD2750 and GO1433, where astronomers need to observe many galaxies simultaneously. By combining detailed spectra with high-resolution images, scientists can construct a complete picture of these ancient galaxies. So, what exactly did scientists observe? These ancient galaxies are very small compared to our Milky Way, with diameters of less than 1,000 parsecs, which is about 1,000th the size of our Milky Way. Despite their small size, they are teeming with activity, a typical feature of young galaxies forming stars in the early universe. Some of these galaxies even exhibit complex structures influenced by gravitational lensing. Gravitational lensing refers to a massive foreground object. Distorting the light from background objects allows us to observe them in greater detail than normal. But why are these size differences significant? It is precisely these galaxies' small sizes that indicate they are in the early stages of evolution. In a young universe, galaxies are still forming and emerging, leading to a peak in star formation activity. These compact galaxies are like snapshots of the early universe, showing us how galaxies originated and grew over time. What do these galaxies look like? For example, HSC 43833 resembles a bright compact object, showing signs of regions with intense star formation, while HSC 16943, although smaller, also shows signs of active star formation. In contrast, MAX 0647 presents a more complex morphology due to gravitational lensing, as the same galaxy appears as multiple images. However, understanding the light from these galaxies is key to unlocking their mysteries. This involves the spectral energy distribution, which represents the range of energies emitted by the galaxy at different wavelengths, from ultraviolet to infrared. By studying the spectral energy distribution, astronomers can infer various physical properties of the galaxies, such as age, mass, and star formation rate. We utilize data from the near-infrared spectrograph and the mid-infrared instrument on the James Webb Space Telescope to create models, followed by using simulation software to explore different scenarios of galaxy formation and evolution. By matching observational data with these models, we can estimate the stellar mass of the galaxies, their star formation history, and other essential parameters. The data from these galaxies indicate that their stellar populations are relatively young, with intense star formation occurring less than 100 million years ago. Detailed analysis of these data helps us piece together the life stories of these ancient galaxies. As we have already mentioned, the light from these distant galaxies is rich in information, especially in the form of emission lines. Emission lines are bright lines that appear at specific wavelengths in the spectrum. When elements in the gas of a galaxy are excited and emit light, they produce a unique set of lines, just like fingerprints, allowing us to determine the chemical composition of the galaxies. In addition to identifying elements, emission lines also reveal the physical properties of the galaxy's gas and stars. By analyzing the intensity and ratios of these lines, astronomers can estimate the star formation rate, indicating how many new stars are being born in the galaxy. For example, a high star formation rate, indicated by emission lines, means that the galaxy is actively producing new stars. Emission lines also help determine the oxygen content of the galaxy, which is an indirect indicator of its overall metallicity, telling us how many generations of stars have existed. Over time, these stars enrich the galaxy with heavier elements. Understanding these properties helps compile a history of the galaxy and determine its evolutionary stage. One of the most interesting features observed in these distant galaxies is the presence of damped Lyman alpha DLA absorption. But what exactly is DLA? In simple terms, DLA is a broad absorption feature in the spectra of galaxies caused by the presence of large amounts of neutral hydrogen gas. This absorption line is much wider than normal lines, indicating the presence of substantial gas. DLA is important because it allows us to directly measure the neutral hydrogen content in the early universe. This information helps us understand how galaxies acquire the gas that fuels star formation and how they evolve. By studying DLA, we can gain insights into the conditions in the early universe that led to galaxy formation. Detecting DLA in these galaxies requires analyzing their spectra to look for characteristic broad absorption features. This process enables us to quantify the amount of gas present and understand the environment surrounding young galaxies. The presence of DLA in these galaxies tells us that they are rich in neutral hydrogen, which is crucial for star formation. It also provides insights into the intergalactic medium and the role of gas in galaxy formation. By comparing the DLA characteristics of different galaxies, we can construct a more complete picture of the early universe. The discoveries of these ancient galaxies offer us a unique opportunity to compare them with other known ultraluminous galaxies. Unlike more evolved galaxies, these newly discovered galaxies have unique features that set them apart. What makes these newly discovered galaxies special is the presence of an unusually high amount of dense gas around them. This gas, primarily composed of hydrogen and helium, is one of the earliest elements to exist in the universe. The presence of such dense gas is unusual because it indicates that these galaxies are in the earliest stages of evolution, and this dense gas may play a crucial role in providing the fuel for the formation of new stars in their evolution. Another unique feature of these galaxies is their low metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium in a galaxy. Low metallicity also confirms that these galaxies have not undergone many cycles of star formation, meaning they contain fewer heavy elements and are in the earliest stages of evolution. Therefore, they are ideal laboratories for studying the initial phases of star formation and their evolution. This information will help us piece together the sequence of events that led to the formation of galaxies in the early universe. These discoveries also fit into a broader context of understanding cosmic history during the so-called epoch of reionization, when the universe transitioned from opaque to transparent. The galaxies discovered by the James Webb Space Telescope are among the earliest to contribute to this reionization process, ionizing the surrounding gas. The next step will involve creating a statistical sample of a large number of galaxies to estimate the universality and brightness of their characteristics. Researchers will continue to study the location of gas near the centers of galaxies, its content, and whether it is primordial gas or has already incorporated heavier elements. Perhaps in the near future, we will see the latest results and discoveries from scientists. The structure of the universe is woven from clues formed over time, or is it just an unattainable dream? Next, we continue to complete this exploration between science and imagination, unveiling the boundaries of our understanding of the universe and our place within it. Can we bend time at will, just like instantly traveling from one destination to another, or setting time to freely traverse our past and future? Next, let's explore the enticing concept of time travel, delving into the realms of physics and fantasy to reveal whether our universe holds the potential for such temporal journeys. What barriers exist between us and the realization of a warp drive engine, a technology that might break the cosmic speed limits set by Einstein's theory of relativity? Together, we will understand the scientific obstacles and breakthroughs that suggest the possibility of superluminal travel. What prevents us from constructing a warp drive? In the grand cosmic events of star formation and black hole consumption, the concept of oscillation presents a relatively paradoxical conclusion. This is a seemingly impossible idea, yet one that carries potential, challenging our understanding of astrophysical phenomena. Do these theoretically opposite celestial bodies really exist? Do they eject matter and light into the cosmos? What do their discoveries mean for our understanding of cosmic evolution? Finally, we turn to groundbreaking discoveries that connect physics and biology through a new natural law, providing a framework for predicting evolutionary processes. How does this new natural law redefine our understanding of the complexity of life and its interactions with the physical universe? Imagine a stone-carved canvas woven from the threads of time, where matter extends infinitely in all directions, capturing every choice, every event, every heartbeat. What if you could traverse this intricate canvas? What if you could go back to the past, witness the future, or even alter the course of history? Time governs our lives, yet it remains one of the most mysterious phenomena in the universe. We measure it and chase it, but can we control it? The concept of time travel has fascinated humanity for generations, inspiring countless works of science fiction and sparking intense debates. But what does science have to say? Can time travel leap from the pages of science fiction into the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility, suggesting that time is not a constant but a variable that can be manipulated. Furthermore, black holes. Such cosmic phenomena are so powerful that they can not only warp light but also bend time itself. Perhaps you are unaware that astronauts on the space station age more slowly than people on Earth, even if only by a fraction of a second. This is not science fiction. It is a verified result of high-speed travel. So, let us embark on this journey through the corridors of time, discovering the scientific theories and the boundless possibilities that may one day make time travel a reality. Long before the scientific knowledge we know today, humanity has been fascinated by the sky and the passage of time. Ancient civilizations paid close attention to stars, the sun, and the moon, meticulously crafting calendars and methods to measure time. In modern times, this fascination finds new expressions in films and literature. The concept of time travel has been a recurring theme, providing both an escape from reality and a platform for intellectual exploration. In 1895, H.G. Wells wrote a novel about the concepts of time and dimensions called The Time Machine. By the way, this novel not only popularized the term time machine, but also introduced the idea that time could be traversed like a spatial dimension. Soon after, Back to the Future, a pop culture film, brought the concept of time travel to a whole new generation. Who could forget the DeLorean car, the flux capacitor, and Doc Brown's charming eccentricity? But this is not just a Western phenomenon. The allure of time travel transcends cultural and linguistic boundaries, resonating with storytellers around the world. So what draws storytellers to focus on this concept? Is it the temptation to rewrite history, the illusion of the unknown, or the philosophical questions these journeys provoke? It is a desire interwoven with nostalgia. One of the contributing factors is the galaxies they are surrounded by, filled with ionized gas. The next step will involve creating a statistical sample of a large number of galaxies to estimate their characteristics and brightness in detail. Researchers will continue to study the position of gas near the center of galaxies, whether it is primordial gas or has already contained heavier elements. Perhaps in the near future, we can see the latest results and discoveries of scientists. The structure of the universe is woven from clues that unfold over time. Or is it just an unattainable dream, a companion of aspirations? Next, we continue to explore this connection between science and imagination, revealing the boundaries of our understanding of the universe and our place within it. Can we bend time at will, just like instantly traveling from one destination to another? Or set the time and freely traverse our past and future? Next, let's explore the alluring concept of time travel, delving into the realms of physics and fantasy to uncover whether our universe holds the potential for such temporal journeys as we aim to realize a warp drive, a technology that might break through the cosmic speed limits set by Einstein's relativity. What obstacles exist between us and this goal? Together, we will understand the implications of superluminal travel, the scientific barriers and breakthroughs of this possibility, pondering what prevents us from building a warp drive. In the events of cosmic phenomena, such as the birth of stars and the swallowing of black holes, the concept of oscillation presents a relative conclusion. This is a concept that seems impossible yet holds potential. challenging our understanding of astrophysical phenomena. Do these celestial bodies, theoretically opposite to black holes, really exist? Do they spew matter and light into the universe? What does their discovery mean for our understanding of cosmic evolution? Finally, we turn toward groundbreaking discoveries. A new natural law connecting physics and biology. It provides a framework for predicting the processes of evolution and how this new natural law redefines our understanding of the complexity of life and its interaction with the physical universe. Imagine a tapestry woven from the threads of time. Matter extends infinitely in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate tapestry? What if you could go back to the past, see the future, or even change the course of history? Time governs our lives, yet remains one of the most mysterious phenomena in the universe. We measure it, chase it, but can we control it? The concept of time travel has captivated humanity for generations, inspiring countless works of science fiction and sparking intense debate. But what does science say? Can time travel leap from the pages of fiction into the annals of scientific fact? Einstein's relativity opened the door to this possibility. He showed that time is not a constant, but a variable that can be manipulated. Furthermore, black holes are such powerful cosmic phenomena that they not only warp light, but also distort time itself. Perhaps unbeknownst to many, astronauts aboard space stations age more slowly than people on Earth. Even if it's just by a fraction of a second, this is not science fiction. It's a proven result of high-speed travel. So let us embark on this journey through the corridors of time and discover that science offers infinite possibilities that might make time travel a reality one day. For a long time before the science we know appeared, humanity has been fascinated by the sky and the passage of time. Ancient civilizations focused on stars, the sun, and the moon, meticulously crafting calendars and methods for measuring time. In modern times, this fascination has found new expressions in film and literature. The concept of time's passage has been a recurring theme, providing both an escape from reality and a platform for intellectual exploration. In 1895, H.G. Wells wrote a novel about time and the concept of dimensions called The Time Machine. Just to share a bit of knowledge, this novel popularized the term time machine and introduced the idea that time could be traversed like a spatial dimension. Shortly after, Back to the Future brought the concept of time travel to a new generation in popular culture. Who could forget the DeLorean car, the flux capacitor, and Doc Brown's charming eccentricity? But this is not just a Western phenomenon. The allure of time travel transcends cultural and linguistic boundaries, and the theme of time travel resonates with storytellers around the world. So what attracts these storytellers to this concept? Is it the temptation to rewrite history, the illusion of the unknown, or the philosophical questions these journeys provoke? It's a desire woven from nostalgia and anticipation, a longing to relive those precious moments lost, or to leap into the promises of the future. As we stand at the forefront of scientific discovery, these findings may turn dreams into reality. This question becomes more pressing than ever. Should we, or if we truly could time travel, what would happen? The blackboard is a canvas where abstract equations become possible. Equations like this are not just symbols. They are keys to understanding the universe. But can they unlock the secrets of time travel? From the screen to living room TVs, time travel has been depicted in countless works. But let's peel back the layers of fiction. A deep exploration of time's fulfillment is not just a science of plot settings. Let's get to know space-time, the structure of thought in our universe, according to Einstein's relativity. This structure can be curved and distorted by mass and energy, but can it be torn or twisted? Can it create a path through time? Time dilation is one result of Einstein's theory. It suggests that the speed at which time passes can vary based on the speed of motion or the strength of a gravitational field. For example, astronauts on the space station age slightly slower than people on Earth. Particle accelerators and experiments within atoms provide empirical evidence for time dilation. Observations show that particles moving close to the speed of light decay more slowly than stationary particles. Additionally, there are wormholes, hypothetical tunnels in space-time that could theoretically shorten time and space. Though somewhat speculative, the mathematics suggests they are possible. Leading physicists and cosmologists have expressed opinions, proposing various theories ranging from plausible to bizarre. Some even believe quantum mechanics, the science of the microscopic world, may play a role in making time travel possible. And let's not forget, black holes. These mysterious cosmic behemoths have such immense gravity that they can not only distort space, but also time itself. Perhaps these cosmic phenomena could be gateways to other eras. However, there is no consensus in the scientific community. Time travel presents challenges to the foundations of physics. From the nature of reality to the concept of causality, it is said that time always flows forward and never backward. But what if we could leap forward, skipping years, decades, or even centuries? This idea may not be as far-fetched as it seems when it comes to slowing down time. Speed would be a major factor. According to Einstein's relativity, the faster you move through space, the slower you move through time. Therefore, extreme speeds might open the door to the future. So, has time travel to the future already been achieved? The scale may be very small right now, but this case might make you reflect on the experiences of astronauts on the space station who age more slowly than their peers on Earth. Let's turn our attention to the twin paradox, a famous thought experiment that elevates time dilation to a new level. Imagine a pair of twins separated at birth, one traveling through space at near light speed while the other stays on Earth. When they reunite, the twin who traveled in space will appear younger. Achieving near light speed would significantly enhance this effect. However, such speeds are currently beyond our technical capabilities, not to mention the energy required would be massive. Scientists and engineers are working to solve these problems, researching propulsion technologies that may one day make near light speed travel possible. Even so, according to current human physiology, it is difficult to endure such a journey. But what if time dilation capsules became as common as airplanes? Humanity could leap into the future to glimpse advanced civilizations or even avoid disasters. Would knowledge of the future be a gift or a curse? What would it mean for the concept of free will? From science fiction to scientific articles, wormholes have captured our collective imagination. These hypothetical tunnels in space-time could become the cosmic shortcuts we've always dreamed of. But what are wormholes? Could they be the key to time travel? If you fold a piece of paper to bring 2 points together and poke a hole in it, a wormhole acts like that pencil, creating a straight path between two distant points in space-time. This concept has garnered attention in the scientific community, partly due to Carl Sagan and the physicist Kip Thorne, who consulted on his novels to explore the scientific possibilities of using wormholes for interstellar travel. Today, physicists are delving deeper into the mathematical principles of wormholes. Although general relativity allows for their existence, the equations also suggest they would collapse so quickly that nothing could pass through. Theoretically, introducing some exotic matter, for example, could counteract the gravitational forces that cause wormholes to collapse, keeping them open long enough for objects or people to pass through. In popular media, depictions of wormholes often overlook these complexities. They are typically portrayed as stable, glowing vortices. But in reality, if they exist, they might be much more unstable and unpredictable. If wormholes could be used for time travel, one end could be anchored in the present, while the other end is in the future or past. Would it be a gift or a curse? What does it mean for the concept of free will? As we approach the potential discovery of these cosmic shortcuts, we must ask ourselves if we are ready.